We now introduce the one-way analysis of variance, also called ANOVA, which is a tool to analyze the results of an experiment. In practice, numerous situations involve more than two levels of interest or multiple factors of simultaneous interest. ANOVA serves as the appropriate analytical method for this type of experiment. The objective of ANOVA is to analyze the effect of K treatment of one factor, for example, sales strategies, on a response variable, for example, sales team's performance. ANOVA was first developed for use in agriculture, where the term treatment was used to identify how different plots of land were treated with various fertilizers. One-way ANOVA is now commonly used in many fields, including psychology, biology, and business, to compare the means of different groups and determine if there are significant differences between them. To conduct one-way ANOVA, we need to find the mean and standard deviation of all possible values of the response variables for each treatment. Specifically, for treatment I, we calculate the treatment mean, mu I. One-way ANOVA estimates and compares the effect of the different treatment on the response variables by estimating and comparing the treatment means mu1, mu2, and mu-k. In this example, Joyce, who manages a regional financial center, wants to assess and compare the productivity of 3 employees based on the numbers of customers served. To achieve this, she selects 4 days at random and records the number of customers served by each employee. The goal is to determine if there's a significant difference in the mean number of customers served among the employees. The data are shown on the right-hand side. Suppose there's no difference in the treatment means. This will indicate the population means are the same. This is shown in the chart on the bottom left. Note that the populations follow the normal distribution, and the variation in each of the population is the same. The chart in the bottom right illustrates how the populations would appear if there were a difference in the treatment means. Again, the distributions follow the normal distribution, and the variation in each population is the same, but the means are not the same. By conducting one-way ANOVA, we can estimate and compare treatment means mu1, mu2, mu3 to mu-k to determine if significant difference in the response variables exists across various treatments. In an experiment with K treatment, the null hypothesis states that all treatment means are equal. If the null hypothesis x0 is rejected, we cannot conclude that all treatment means are equal. Rejecting h0 implies that at least 2 treatment means differed significantly in their values. Conceptually, if the null hypothesis h0 is true, then the means of different treatment originate from the same sampling distribution. In this graphical representation of the sampling distribution, the means of 3 treatment emerges from a common distribution. However, if the null hypothesis H0 is false, then the means of different treatment originate from distinct sampling distributions. For instance, in this graphical representation, each treatment mean belongs to a separate sampling distribution. When comparing these two representative graphs, we can infer that if the null hypothesis H0 is true, then the between treatment variability, which is the variance between the treatment means from treatment sample to treatment sample, is smaller than when H1 is true. Consequently, one approach to determine whether treatment means exhibit significant differences is by evaluating the between treatment variability relative to the within treatment variability. The variability between treatment pertains to the fluctuation of sample means across different samples, whereas the variability within treatment refers to the fluctuation of values within each individual sample. If H0 is true, the ratio of between treatment variability to within treatment variability should not be considerably large. ANOVA can be viewed as the process of partitioning the total sum of squares and the degrees of freedom into their corresponding sources, treatments, and error. The total sum of squares, SST, is the overall sample variance that would be obtained if we treated the entire set of observations as one data set. With the entire data set as one sample, the formula for computing SST is given by summing the squared differences between each value and the overall mean. The variation due to treatment, SSTR, is also called variation between treatment means. If the treatment means are similar, this value will be small. The smallest possible value will be 0. The SSTR is given by summing the squared differences between each treatment mean and the overall mean, and then multiplying each squared difference by the number of observations in each treatment. Random variation is also referred to as the error component, and is also called the variation within the treatment, SSE. The SSE is given by summing the squared differences between each value and the mean for each treatment. Therefore, we have SST equals SSTR plus SSE. The F-test in ANOVA is used to determine if there's a significant difference between the means of 3 or more treatments. It compares the variation between the means of the treatment, also known as the treatment effect, to the variation within the groups, also known as the error effect. The F statistic is calculated as the ratio of the variance between treatment to the variance within treatment. Mathematically, it is MSTR divided by MSE. MSTR is the mean square due to treatment, which is calculated as SSTR divided by its degrees of freedom, k-1. And MSE is the mean square error, which is calculated as SSE divided by its degrees of freedom, n-k, where n is the sum of all samples. If the F statistic is greater than the critical value, we reject the null hypothesis and conclude that at least one of the group's means is different from the others. The F-test is commonly used in experimental research to compare the effectiveness of different treatment or interventions. We again use a graph to further demonstrate the F distribution. The p-value is the area under the F curve to the right of F distribution, where the F curve has k-1 numerator and n-k denominator degrees of freedom. The F critical value, F alpha, can also be obtained by Excel function. That is, F alpha equals f.inv.rt in terms of alpha, k-1, and k. If f larger than f alpha, then we reject H0 in favor of HA at the alpha level of significance. Or if the p-value is smaller than the chosen significance level, for example, alpha equals 0.05, then the null hypothesis is rejected, and it is concluded that there's evidence of a significant difference between at least two of the treatment means. An ANOVA table is a statistical table used to analyze the result of an ANOVA test. It summarizes the sources of variation in the data and tests the null hypothesis that the means of multiple groups are equal. The table is typically divided into 4 parts. The first part, the sum of squares, SS column, which shows the total sum of squares and the sums of squares for each source of variation, that is, treatment, error, and total. The second part, the degrees of freedom, DF column, which shows the degrees of freedom for each source of variation. The third part, the mean square MS column, which shows the mean square for each source of variation. The fourth part, the F statistical and p-value column, which shows the F statistical calculated by dividing the treatment mean square by the error mean square and the corresponding p-value. If the F value is larger than the F critical value, or if the p-value is less than the significance level, usually 0.05, the null hypothesis is rejected, and it is concluded that there's a significant difference between at least two of the treatment groups.